Now on to C4. Now for each of the following, we either say the proof is the statement is true and prove it, or provide a counterexample for why it's false. Now, the first one we have, and we're given that the hint is they're all false. So because they're all false, then what we want to do is we want to look at what t of 0 does, and we want to say, okay, then t is a linear transformation. Well, if I consider t of x equaling x squared. Now this is the example, but this is a valid counterexample, but I haven't proven it's a valid counter. So t of 1 plus 1 equals t of 2, which equals 2 squared, which equals 4. T of 1 plus t of 1 equals 1 squared plus 1 squared equals 1 plus 1 equals 2, which does not equal 4. Thus, t of 1 plus 1 does not equal t of 1 plus t1. Therefore, t is not closed under addition. However, t of 0 equals 0 squared equals 0. So it satisfies the condition, but it's not a linear transformation. Now we have let V be a vector space, and V has a spanning set with an infinite number of elements. Then V is finite dimension. Well, let V equal the span, or let V equal R, and S equal R. Then S has an infinite number of elements, but the dimension R equals 1. And here's our counter. Now, t squared equals t. Then t is either the identity or the 0 transformation. Well, if I consider 1, 0, 0, 0, then 1, 0, 0, 0 times 1, 0, 0, 0 equals 1, 0, 0, 0. Or t of x, y equals x, 0. T of t of x, y equals t of x, 0, which equals x, 0. Thus, t squared equals t, but t is not the identity or the 0 transformation. These examples take a little bit. You got to figure out what the example is, but then you also need to show it. You need to justify why it's about. The last one is let W1 and W2 be a subspace, then W1 union with W2 is a subspace. Well, if we do this, then let W1 equal the span of the set 1, 0, set containing the vector 1, 0, and W2 equal the span of the set containing 0, 1. Then consider W1, or then consider 1, 0 plus 0, 1. Which equals 1, 1. Note, 1, 1 is not in the span of the set containing 1, 0. And 1, 1 is not in the span of the set containing 0, 1. Thus, 1, 1 is not in the span, the set containing 1, 0, union with the span of the set containing 0, 1. So 1, 1 is not in W1 union W2. Since 1, 0 was in W1 union W2 and 0, 1 is in W1 union W2, this set is not closed under addition. Therefore, it is not a vector space or a subspace. Now for C5. Now we have let V and W be vector space. Suppose T maps V to W. Under which condition can a linear transformation exist such that T is both injective and surjective? Well, this is the dimension of V equals the dimension of W. Now, given these conditions, prove that T is injective if and only if T is surjective. Well, T is injective implies that kernel of T equals the 0 vector, which implies that the dimension of the kernel T equals 0, as the dimension of V equals the dimension of the kernel T. I should add equals n here, plus the dimension of the image of T, which equals n, and the dimension of the kernel T equals 0. The dimension of the image T equals n, which equals the dimension W. Thus, T is surjective. Now, the reverse argument is similar, and I'm going to leave that as an exercise. Going in the reverse direction is very similar, but you start with surjective, and then you get the dimension W equals the dimension of the image, which is n. You use your rank nullity, you get your kernel, and you get injective.